So we will start in 3 minutes time. I think 3 more people are yet to join. 3 or 4 more people are yet to join. Just a minute. Hello? Huh? হ্যাঁ আচ্ছা পাঠিয়ে দিন। Okay, so because it's a power diode, so the total current and voltage handling capacitors are different. Mainly the current handling capacitors, so you have to make necessary heat sink arrangements and so on and so forth. Unfortunately, I can't show you directly because it's a virtual lab. You cannot go to the lab and check what is there as components. Anyway, the point is when we use a silicon diode and use it as a rectifier in a rectification circuitry, we know that the diode is having VI characteristics, which is basically something which looks like I equal to I into to the power minus some constant into V, where this I is the diode current and the constant depends upon so many factors, and V is the voltage across the anode cathode junction of the diode. Okay. Now, if I plot the transfer characteristics, it's current versus the voltage, I versus V. Now, if it looks like an exponentially rising curve, then the main problem is how do we use this particular element in a circuit? Okay. For example, a full wave rectifier is a circuit, and we need to analyze the circuit to find out what are the essential components of current and voltage across and through each and every component in the circuit. Okay. So there, if I have a nonlinear element, nonlinear in the sense that the VI characteristics is not a linear equation, then it becomes difficult to find out what is the current, because this does not have a very simple equation like expression. It's something I0 e to the power q e to the power e to the power qv. Q is a constant minus 1. Okay, I0 is the reverse saturation current. So here what we plan to do is, if you can replace this by a linear equation y equal to mx plus c, that means if I know the voltage, I can immediately predict what is my current. Then circuit analysis becomes simpler. Okay. So here what we do, if I look at the VI characteristics of a diode, then we find that there are two distinct regions. One, which is before V gamma, the cut-in voltage of the diode, and second, which is after V gamma, that means beyond the cut-in region. So the diode current gradually increases from 0 to a certain small value when the diode voltage, that means voltage across the anode cathode junction of the diode, is less than V gamma, the cut-in voltage. But once it exceeds V gamma, then current grows exponentially. Clear? So what we will do, we will try to replace these two regions by two straight line pieces. Okay. So that is what is meant by two-part piecewise linear model of a rectifier diode. So in the process, we will find out what is the diode current for a particular voltage, right? For two regions, one where the diode voltage is less than V gamma, that's the first region, and the second region is when the diode voltage is more than V gamma. Okay. So for these two regions, we will find out a few handful of points experimentally. Clear? And from these points, we will draw straight line fits. Okay. Now, how do we generate straight line fits? There are many methods. But the simplest of them is to write a least square fit, linear least square fit. So that's what you have to do. You have to write the corresponding program, or maybe you can work it out also on a piece of paper, because there will be hardly 4 to 5 points, and find out what is the corresponding values of M and C, which describes the particular portion of the curve as y equal to mx plus c. So this straight line approximation is very important. So what will happen then? Then what will happen if you extrapolate both the straight lines so that they cut at a particular point, then the x-axis intercept of that particular point, or maybe the x value of that particular point, will give you a measure of V gamma. That is, what is the voltage to be impressed across the diode so that it cuts in, okay, and it conducts. Right? So if you have two straight lines, then the intersecting point gives you what is your V gamma. Okay? And what is the second part? When the diode is in the conduction region, that means the diode voltage is greater than V gamma, then it's a second equation, y equal to mx plus c. Now here what is m? M is slope of the line. Now if you look at the axis, then the y-axis is current and x-axis is voltage. So the slope of the line is essentially the conductance, or maybe the uh, conductance value of the diode in the conducting region. Okay. So the reciprocal of the slope, that means if you find out what is your M, then 1 by M will give you the dynamic resistance of the diode. There's the diode resistance when it is conducting, right? So it's essentially a simplification. Otherwise, what you could have done, I mean, that would have made your life miserable, is at each and every operating point, you find out what is slope to that particular line, diode curve. And from the reciprocal value of the slope, you find out what is the current diode resistance. That means if you follow this particular method, then diode resistance is not a constant value. It varies over time depending upon at what particular current you are operating. Clear? Now this is a difficult proposition. In circuit analysis, we do not want to impose so many constraints in finding out what is the current for a given voltage. Okay. Instead, we replace the diode by a simple model consisting of a power supply and a resistance, which is fixed over the entire region of operation. Clear? So that's the basic motivation for replacing the diode characteristics by a two-part piecewise linear model. Am I clear? Any query, class? পাবেল তুমি একটু পরে জয়েন করেছো, আমি জাস্ট এক্সপেরিমেন্টটা বলতে শুরু করেছি। হ্যাঁ, তাহলে আমি বেশি দূর এগোই নি। আমরা কি করে ডায়োডের ট্রান্সফার ক্যারেক্টারিস্টিক্স which looks like an exponential growing curve তাকে দুটো লিনিয়ার সেকশনে ভাগ করে ফেলবো সেটা বলেছি। এবং once we find these two linear sections we can find out from the graph what is my cutting voltage first and what is the dynamic resistance of diode when it's conducting. ঠিক আছে,
ঠিক আছে স্যার।
ওকে, কোনো কোয়েরি আছে ক্লাস? কাল কোনো কোয়েরি আছে? সৌম্য কোনো কোয়েরি আছে? সৌম্য জয়েন করে পালিয়েছে। স্নিগ্ধা, is it okay? Okay. Shivam, is it okay?
Yes, sir.
Okay. So if you have a query, you please ask it, or you may type your queries in the chat box. Right? Even if you feel it's okay with you, you simply write okay, then we can proceed. Because unless I get some feedback from the class, it's difficult for me to assess whether you're understanding it or not. It's a very simple mechanism, but still, it's part of the lab, of the entire process. Clear? So we once again go back to the presentation part. So if I look at the circuitry, how to find it out, then please concentrate on figure 1. So what we have with us, or the instruments that are involved are a DC variable power supply for which the current can be limited. Okay. So how do we limit the current of a power supply? You essentially dead short the two terminals of the power supply, right? So ideally an infinite current should flow, and if the current exceeds the maybe the fuse put in the device, then definitely the fuse will blow. Clear? Because ideally finite voltage divided by a zero resistance path, right, should give you infinite current. That means the fuse should blow. But what is being done in this power supply is there is some control mechanism through which I can fix the current that can be drawn from the power supply even in short circuit to a predefined value. So there's a knob. So using the knob, you can set the current limit. So here what we do, we pick up one such power supply where this current limiting facility is inbuilt, right? Now this particular voltage is kept at 1.8 volt, right? So this entire experiment uses two different diodes. One a normal silicon power diode, rectifying diode, and the second one is a Schottky diode. Now, if you go through standard textbooks, which are written at least some 20 years back, there was a second variety of popular diode, which is called the Germanium diode. The silicon diode and the Germanium diode. The diamond diodes, they have become, or maybe Germanium devices, they have become gradually obsolete because of many reasons. So same is true for Germanium diodes and transistors. So the difference between those two, they are the cut-in voltages. Germanium, for silicon, it's 0.7 volt, as you know, but for germanium, it's less. It's around 0.3 volt, right? So here, since we do not have access to a germanium diode, what we have used is a Schottky diode. So Schottky is basically a diode where the junction is a metal semiconductor junction. Okay, so maybe the anode is metal and the cathode is a semiconductor material, made of a semiconductor material. So advantage is it switches faster, and second thing is the forward path drop, that means V gamma, when the diode is conducting, is also pretty small. It's the order of 3 to 3.5 volts. Okay, so we will use these two varieties in the same circuitry. That means we'll pick up one, we'll connect it directly across the power supply, right? So there is no chance of the power supply being shorted and excessive current flowing through device and thereby damaging the device, because you can limit the current. We'll limit the current from 1 ampere to 5 amperes. Okay, but simply think of the fact that the 5 ampere current, okay, multiplied by what is the power dissipated? It's V square by R, okay, or maybe I square R. So if I is pretty large, therefore any particular R, right, the heat dissipated across the junction will be very high. Clear? So that's why we find that all these devices, they come with proper heat sinks, right? So that the junction is not really destroyed. In this particular case, the procedure says, I'll go through it slowly. The procedure says you connect a you set the power supply to 1.8 volt. So now if I connect a diode directly to 1.8 volt, then what will happen? It will eat up, say if it's a silicon diode, it will eat up 0.7 volt to overcome the cut-in voltage, right? Then the next, that means that 1.5 minus 0.7 is 0.8, divided by the diode resistance will be the diode current. So the voltage and current requirement, they need to be taken care of, or should I put it in some other, in other words, the current limiter in the power supply should be properly tuned so that no excess current or no current beyond the rated values given by the manufacturer should flow to the devices. Okay. So what we'll do, if I put a 1.8 volt power supply, and then if I program the power supply output to be 1.8 volt, and if I connect a diode whose cut-in voltage is 0.7 volts, say a silicon diode, then what will happen? A huge amount of current will flow through it. So what we will do, initially, we will set the current limit to 1 ampere. Okay, so whatever be the excess voltage, a 1 ampere current will always flow through the diode. Right? Now 1 ampere is no joke. Okay, so if I want to find out what is the drop across the junction, PN junction, then instead of reading the data from the power supply display, because actually whatever is the power supply display is the voltage applied across the diode. If it draws a good amount of current, then what will happen? Depending upon the power rating of the power supply, the voltage will go down. Okay, because V into I should be a constant for a given power supply. Clear? It can draw more current, but if it draws more current, then what will happen? V should go down naturally so that this V into I product remains the same. Clear? Now, this particular value of the voltage, you see the voltage comes across the diode itself. If you look at the figure, you see the anode point is connected to plus terminal and the cathode point is connected to the minus terminal. Okay, so that means the diode or maybe the voltage supply reading is what is the voltage applied across the diode. But still, we use a digital voltmeter to read the voltage across the voltage drop across the diode. Okay, the reason is very simple. A diode is connected through wires. That means one wire is coming from the anode, the second wire is coming from the cathode and getting connected to the power supply terminals. Now, when you sink 1 ampere current through the diode, then whatever small be the value of the resistance of the wires, there will be some considerable voltage drop across the wires. Because wire means it's a resistance, its value will be very small. But since you're pumping in 1 ampere of current, through the diode, the drop across these resistance will be pretty high. Now, if you connect a DVM just across the diode terminals, then you can measure the exact voltage across the diode terminals. So what we'll do, we'll record these two, right? Now, here you see the trick is you fix a current and pump it to the diode, and then using the DVM, you find out what is the voltage drop across the diode. So that means for 1 ampere current, I can read. So you have to record it in a tabular form. It's given over here. So what is the forward voltage drop across the diode for a particular forward current? So for 1 ampere current, what is the voltage drop? Okay. So now what we'll do, you will proceed. You will gradually increase the current pumped through this particular diode in steps of 1 ampere. That means you will start with 1 ampere, go to 2 ampere, then 3 ampere. How do you change it? So there is a current limiter switch, right? So you can set it to 1 ampere, then to 2 ampere, then to 3 ampere, and up to 5 ampere. Okay. So for each such value of the set current, you read what is the voltage across the diode, voltage drop across the diode using the DVM. So that means we have 5 points. We have 5 defined points in region B. What is region B? Region B is defined for voltages which is more than the cut-in voltage of the particular diode. Clear? So for that, for a silicon diode, the cut-in voltage is always 0.7 volt. I've impressed a power supply. I've impressed a voltage which is equal to 1.8 volt across the diode. So the voltage across the diode, impressed across the diode, is good enough to take it to the conduction region. Am I clear? So from these 5 points, you can draw the one section of the diode curve. Okay. But this section, instead of drawing the curve, you have to write down what is the approximate straight line fit through these points. So how do you find out the approximate straight line fit? You use a simple algorithm called the least square error method. Okay. So what is least square error method? Since you have measured, you know what is your y and for a given x. That means what is the diode voltage for a diode current. Okay. Now, what you assume is this diode current is basically a function of the diode voltage and some constant. Clear? So that's your equation. Current is equal to some slope value m into voltage plus some constant value c. So that's y equal to mx plus c. That's a straight line fit. Okay. So obviously, what is the error? Because if you assume that the particular straight line is not a curved line, but is approximated by a straight line, then obviously the actual data and the computed data will have some difference, and that is being predicted as the error. So for each point, you have an error which is given by the actual data, right, minus mx plus c, because that's the straight line approximate value for the corresponding point. So this error is squared and they're added up. So we have E1 square, E2 square, E3 square, E4 square. What does this 1, 2, 3, 4 mean? 1, 2, 3, 4 mean these are the current values at which we have taken the data or the reading. Clear? So we have this error function, right, defined in terms of variable which are m and c, slope of the proposed straight line fit and the y-axis intercept of that particular straight line. Okay, so it will look like an equation involving m and c. Now what you have to do, you have to find out for what m and what c, the summation of the square of error is minimum, right? So that's how we will find out. So what is the method? You simply differentiate these two equations and you will form two partial equations. The first one is dE by dC, where m is taken to be constant, and the second one is dE by dm, where c is taken to be constant. So once you take the slope to be constant, and the second one you take the error y equal to mx plus c. Okay. So the second part, what is m? M is, or the reciprocal m is the dynamic resistance of the diode. Okay. So we have two differential equations, and solving them, we have to find out what is my c and what is my m. So you later on, when you analyze the circuit, you use these values of m and c to define the diode straight line model. Am I clear? So once again, you have to go back and write down what I have said in a piece of paper and find out whether it's okay or not, right? So then using a standard MATLAB package, I think it's already with you, right? So the standard MATLAB package, you write the corresponding equation, right? So you assume the diode to be a linear device given by an equation y equal to mx plus c. You have 5 test points, which are real life data taken in the lab, and from this 5 test points, you find out what is your m and what is your c. Clear? Then what happens? Then we come to the second part of the piecewise linear model, namely the part where the conduction is yet to begin, or even if it starts, the current is very small because we have not crossed phi gamma. Okay, so there the standard technique is, so it's been given in point 4. Okay, so here the standard technique is, so once again you change the current limit value to 1 ampere, because you have gone up to 5 amperes by changing the current limit values. Now you change it back to 1 ampere, right? So the maximum current that can flow through the diode is 1 ampere. Okay. And we have already applied a voltage of 1.8 volt across the diode. Now by changing the voltage switch, you put it to 0. That means we are trying to find out what is the current at the origin. Obviously it will be 0 because the power supply is 0, right? Now then you change the power supply voltage in steps of 0.2 volt. That means first you impress 0.2 volt, find out what is the current. Then you change it to 0.4 volt, then you change it to 0.6 volt, and then you change it to 0.8 volt to find out what are the currents. Now since the current is limited to 1 ampere, once you go to 0.8 volt, right? And that's because the cut-in voltage of a silicon diode is 0.7 volt. So if you impress a voltage of 0.8 volt across the diode current will clamp to 1 ampere. Because anything beyond its cut-in voltage means the diode becomes almost a short circuit. Okay, so huge amount of current will flow through the diode, but because there is a current clamping mechanism, the maximum current that flows through the diode is 1 ampere. So 0.8 volt is basically an indication that you have crossed from the first region where the diode voltage is less than V gamma to the second region where the diode voltage is greater than V gamma. So obviously we will not pick up 0.8 as a data point, but we'll pick up 0, 0.2, 0.4 and 0.6 as the 4 data points. And from these 4 data points, we'll once again put a straight line fit, right? So if I mark them as section A and section B, then these 2 straight line fits, if extrapolated, will meet at some point. So that is the cutting point. Okay. So you find out what is the X value of that cutting point, and you'll find out what is the corresponding voltage that ensures cutting. Clear? So this is one part of the experiment. Clear? And what is the second part? Second part is to present all this data in tabular form, so on and so forth. Clear? Now, what we'll do now, given this data, we'll find out from graph what is my V gamma, right? And second is, given the data, we'll find out from this graph, the dynamic resistance of the diode. That means what is the average resistance of the diode or average forward path resistance of the diode. So how do we do it? We find out M. Okay, we are solving the straight line equation. So we'll find out M, and the reciprocal of M will be the dynamic resistance, because it's a current versus voltage. So if I take a slope, I'll get what is my dIdV. But instead, we want to find out what is my dVdi. So that's the dynamic resistance. Clear? So from this part of the experiment, we find out the parameters that will model your diode as a linear device, right? What are these parameters? First is V gamma, the cut-in voltage, and second is the dynamic resistance of the diode. Clear? Now, what we do in section 5 and section 6, we change the diode. So this time we pick up a Schottky diode, okay, for which the value of V gamma lies in the range of 3 to 3.5. So the Schottky diode, right, so we put it in the same circuitry and follow the procedures mentioned above, or for this total period of this class, and then find out once again what are the values of V gamma and RT for a Schottky diode. Right. So first we found out what is V gamma and RT for a normal power silicon transistor, right? And the second one is a specialized Schottky diode, and you'll find that the parameters of the Schottky diode, as far as switching is concerned, is definitely better than that of a silicon diode. Okay, clear. So now we come to the next section of the experiment. Now, here we try to analyze how this particular diode will behave as a circuit element. Okay, so that has been the principal motivation of this particular lab. When we take a device, and that particular device, if it's known to be a nonlinear device, just like a diode, then all hell breaks loose. That means people try to find out how to use this particular component and write some analysis note. Okay, so this particular experiment proposes a very simple mechanism. You find out the parameters of the diode by treating it as a linear device. That means you find out what is your M and what is your C, right? Then when you put the circuit, put the diode in the circuit, you find out how it behaves by assuming the circuit model to be linear. Clear? So the same thing is will be done over here. In the first part of the experiment, we found out the diode parameters for both the diode. Now, if you look at the second part of the diagram, I mean figure 2, which shows the second part of the experiment, we are trying to find out the diode current or maybe the circuit current for a half-wave rectifier, right? The different voltage values, and finally, what is the conduction angle of a diode? So ideally, the conduction of a diode appears to be 180 degree because it conducts in the first half cycle, right? And the same diode cannot conduct when there's a polarity reversal. You need to have full wave circuitry to conduct uh, both during the positive half cycle and negative half cycle. But that's not being done over here. What is done instead is, okay, what is done instead is we try to find out what is the conduction angle of the diode. The conduction angle is a very important parameter because the diode, I mean, once again, we come to the basic circuitry. It's a half-wave rectifier configuration. Okay, I think I'm digressing a lot because I'm not really used to take up such labs in a virtual mode. Uh, this circuitry, if you look at it, it's a half-wave rectifier circuitry. Okay, so that means there is a transformer, and you are connected the half-wave rectifier circuitry in the secondary winding of the transformer. So the input, if you measure the input by using a simple analog oscilloscope, two-channel oscilloscope, then these are the test points at which we are taking measurements. One is TP1 and the second is TP2. And we are measuring both the voltages with respect to ground, some defined circuit ground. Okay. So TP1 will be a pure sinusoid because since the input to the system is a sinusoid, the mains power supply. So after step down, right, it will be another sinusoid. Clear? And then what is being done after that? We have put a half-wave rectifier circuitry. So what appears at TP2? At TP2, you will get the half-wave rectified version of the waveform. Okay. So let's draw two figures. Mm, let's go back to this. Okay, can everyone view this Jamboard?
Yes, sir.
Okay. So let's draw the corresponding waveform diagrams. It will not be very smooth, but anyway, it's a freehand drawing. Uh, say this is the axis system, X and Y. X is the time axis and Y is the voltage axis. Okay. So what we'll do, uh, so the secondary winding voltage will be a pure sinusoid. Okay. Clear. But what will happen, since it's a half-wave rectifier circuitry, Okay, since the half-wave rectifier circuitry, আচ্ছা লক্ষ্মীচরণ, তুমি কিন্তু এরকম সময় জয়েন করলে চলবে না, ঠিক আছে?
স্যার স্যার অ্যাকচুয়ালি আজকের দিনটা একটু প্রবলেম হয়ে গেছে, সরি স্যার। এরপর দিন থেকে আমি একদম
ঠিক
সঠিক
আছে,
সময়
টাইমে ঢোকো, নইলে তুমি নিজেই বুঝতে পারবে না কি পড়ানো হচ্ছে।
হ্যাঁ
আর
স্যার,
ল্যাব তো তোমাকে রিপোর্ট করতে হবে এবং তোমাকে ভাইবা দিতে হবে, ঠিক আছে?
ওকে স্যার, আমি পরের দিন থেকে খেয়াল রাখবো।
Okay, so let's go back to the jam board. ঠিক আছে, তো এখানে কি হবে? এখানে the rectified waveform will look like this, তাই তো? The rectified waveform will look like this. That's a typical half-wave rectifier. Okay, so that means it will conduct only in the positive half cycle. It will not conduct in the negative half cycle. ঠিক আছে, এখন এবার যদি ভাবি যে what is the conduction time, then the ideal conduction time, you see it's a power cycle, right? It's a power cycle at the input. So it's a 50 hertz input. So 50 hertz means the corresponding time period is 20 milliseconds. So the first half cycle duration will be 10 milliseconds, and the second half cycle duration will be 10 milliseconds. So if it's an ideal diode where the cut-in voltage is taken to be almost zero, then what happens? The conduction appears to be 180 degrees. That means 10 milliseconds. A full wave means the total angle is 360 degrees, out of which it will conduct only for half the period. That means for 180 degrees. In time scale, this corresponds to the half period of the waveform, which in this case is 10 milliseconds. Am I clear? But actually, because of the cut-in voltage, what happens? Because of this cut-in voltage, what really happens? The conduction part looks like this. Okay, why like this? Because until unless the input voltage exceeds V gamma, the circuit will not work. The diode will not conduct. Okay. Similarly, when this voltage is going down and becoming zero, when the voltage goes below, or it goes below the value of V gamma, which in this case is roughly around 0.7 volt, then once again the conduction will stop. Clear? So that means if I draw straight lines, which is difficult for me to draw, it's a freehand drawing, then what we find is the conduction period is less than 10 milliseconds. Okay, so if you think of these two vertical lines, then a time span between the two vertical lines is 10 milliseconds. Okay, but the time span between these two red vertical lines is definitely less than 10 milliseconds. And this is happening because the diode is not conducting until unless the voltage goes beyond V gamma. So it's very important because it totally changes the power equation or power that's being delivered to the load. Okay, so if you don't know the conduction angle, then you make a wrong estimate of the total power delivered to the load. Because your assumption is the diode is conducting for 180 degrees, only for 10 milliseconds, but the real life scenario says the diode is conducting for a time which is less than 10 milliseconds. So the corresponding conduction angle will be something less than 180 degrees. Okay, so this is very important. Clear? So theoretically, what we do, if you can measure what is the gap between these two lines, so that will be time value, because in an oscilloscope, the x-axis is always a time axis and the y-axis is always the voltage axis. So the space between, or maybe the period between the first black line and the first red line, these two vertical lines, is basically the time for which the diode is not conducting. Similarly, the time gap between the first red vertical line and the second I mean the second line, which is black, is once again the time for which the diode is not conducting. So if I take that these two times is equal to Tg or maybe T gap, then the conduction period for the diode is 10 milliseconds minus 2 into Tg. Clear? So the conduction angle for diode is not exactly 180 degree, it's something less than 180 degree. Clear? So we can always find the time from the oscilloscope plot, but how do we find the angle? It's a simple unitary method conversion. So you write that 10 milliseconds is equal to 180 degrees. So 1 millisecond is equal to 18, uh, 18 degrees. So 10 minus 2 Tg is equal to how much? So first you find out Tg, you find out what is 10 minus Tg, and then you write down what is the conduction angle for this value of Tg. This value of Tg, clear. So that means from the oscilloscope plot, which I'll supply to you, you have to find out what is the exact value of the conduction angle for this particular diode. Am I clear? Class, is it okay? Any query? Okay, so my answer is okay. Yeah. So let's proceed. So this is basically what we will do. I'll give you the values of TP1 and TP2, and from that, what I have to find out is, this is given in 7, right? You have to find out the peak value of supply voltage across diode resistor series combination. So that's the value of TP1. So the TP1, from TP1 you find that, which is sinusoid, you find it was the peak value from the graph, and that's basically your answer to question number 1. And second is, what is the peak output voltage and current? So at TP2, which is the voltage across the load, you look at the waveform, and from that you find out what is the peak value. It will be a half-wave rectified waveform, and from the plot you can find out what is the peak value. It will be a graph with proper latitudes, so that you can find out what is its values using a scale. Clear? And then what is the current? Now this particular wave is across a 10 ohm resistance. Okay. So if I go back, it's a simple 10 ohm resistance over here. So the peak voltage found over here or calculated over here, if that is divided by 10, so that will give you the peak current, right? And then finally, what is the conduction angle? What is the conduction angle? Okay, so let's go to the Jamboard, back to Jamboard. The conduction angle is basically the time between these two red lines. That's the conduction angle. So that's the conduction time. And if you find the conduction time, then immediately you can find out what is the conduction angle. Right? So that's a simple unitary conversion, that 10 millisecond equal to 180 degrees. So what is this time? What is this particular time, conduction period, right? When it gets converted to the corresponding conduction angle value. It's a unitary conversion. So that means you find out what is the conduction time, and multiplied by 18, you will get the conduction angle. Clear? In degrees. Any question? Any query? So here we have a second arrangement. You see, initially the manual says you sketch the waveform and find out these values when the RMS value at the secondary point is 2 volt. And just a few lines below this, right, you're once again required to find out all these values for a secondary voltage of 4 volt. So that means for two different values, you have to find out what are the values of the peak output voltage, right, the peak load voltage, the load current, and the conduction angle. So obviously two queries come into our mind. Why do we take two such different values, right? And second is, the diagram shows that it's a 230 volt, 9 volt step down transformer. So if I apply a 230 volt, okay, if I apply, just give me 1 minute. Huh? Okay, so if we go back to this diagram, right? Maybe this write up. It says that you are required to set the secondary voltage first to 2 volt RMS and then to 4 volt RMS. The transformer is 230 volt 9 volt RMS. Okay, so that's why we have put an auto transformer in front of the transformer. So auto transformer means you apply a 230 volt supply at this point. That's the main supply, and if you change the dial position, then you can get any voltage from 0 to 230 volt at the secondary point of the auto transformer. So that's how your auto transformer works, and that output is connected to the primary of the transformer. So this transformer with the input of 230 volt will give you a 9 volt. So with an input of 115 volt will give you a 4.5 volt. So that's how you can find out the different values of the input for which you will get either a 2 volt or a 4 volt. So that's the basic motivation of having one such circuitry. But the second question is, why a 2 volt and why a 4 volt, right? Why these two different values for finding out the same type of parameters? Okay, to analyze this, we have to go to the circuit once again. Okay, so here you see the conduction starts from this particular point. Okay, now this is a 2 volt sinusoid. Now if I change it to a say, let's change the color. So if I change it to a 4 volt sinusoid, it will look something like this. Sorry, it looks more like a triangular waveform, a rectangular waveform. Anyway, right, forget about the drawing. You assume it to a sinusoid. What we have changed is, we have not changed the frequency. We cannot change the frequency. It's the main frequency. But we have changed the amplitude of the signal. Okay, so what is your reading? So say, if I draw a line, this is your conduction point, okay? So this is 0.7 volt. Okay, so when we have a 2 volt supply, right, then 0.4, 0.7 occurs at this point, this particular time instant. Now if I increase the amplitude, it will occur definitely before this particular line, before this particular time. That means the conduction angle will improve if you increase the amplitude of the secondary waveform, right? So that's basically an observation, right? It appears a bit strange, but the truth is a diode will gradually become an ideal one if you increase the input drive. So if the input drive is small, then the conduction angle will be much less than 108 degrees. But if the input amplitude is pretty high, it goes up to say 230 volt, then the diode behaves like an ideal diode. You cannot find out which particular point it crosses this 0.7 volt. Okay, because if you remember basic mathematics, right, the slope of the sinusoid of any sinusoidal waveform, right, is maximum at the zero crossing point. Okay, so if you if you increase the amplitude, then 0.7 volt will be crossed almost instantaneously, and it will appear to you that the diode is conducting for the entire period of time. So actually it's not true, but it's very difficult to analyze and find that particular point from an oscilloscope. It appears to be a complete 108 degree conduction. Clear? So that's the motivation why two different values are taken for the secondary voltage. Otherwise it's the same. So obviously you have to do it for both. As we have characterized the transfer function, the transfer characteristics of normal power silicon diode and a Schottky diode. Why we choose a Schottky diode? Because Schottky diode, otherwise it behaves like a germanium transistor where the value of V gamma is very small. For a Schottky diode, the value of V gamma lies in the range of 3 to 3.5 volt. Okay, so that means if I go for this experiment with a Schottky diode, that means if I place a Schottky diode over here, right? So what will happen? Definitely we have a better value of the conduction angle, right? Because the first one, the cut-in voltage is 0.7 volt. The second one is something around 0.3 volt. Okay, so that means we will repeat this experiment once with the Schottky diode and the second one with a the silicon diode, right? So how will you do it? This is a virtual lab. So what I'll do, I'll give you the input secondary voltage and the half wave rectified voltage, right? On the same scale, I'll give these two plots. So from this plot will come with proper marking, okay, with proper graticules. So you can read out what are the differences, what are the conduction angles, so on and so forth. And from that, you will find out all these values. Clear? And another thing which I missed is when we are doing this part of the experiment, that's when we are characterizing the diode. Okay, then for a silicon diode, for finding the portion of the curve for which the diode voltage is less than V gamma, we started with 0 volt and then we increased the diode voltage in steps of 0.2 volts. Okay, but when we think of a Schottky diode, or maybe when we think of characterizing a Schottky diode, then for this portion of the curve, we will increase the voltage in steps of 0.1. Because if I increase it in steps of 0.2, we'll get hardly 2 points, 0 and 0.2. When it goes to 0.4, the diode will conduct, right? So for the Schottky diode, we'll pick up points which are 0 volt, 0.1 volt, 0.2 volt, and 0.3 volt. So in both cases, we have 4 such points for the second region, from which we'll find out a straight line curve fit. Clear? Any query, class? Is it okay? So it's given over here. So for the silicon diode, the step was 200 millivolt, that's 0.2 volt. But for the Schottky diode, the step was 100 millivolt, that's 0.1 volt. Clear? Any query, class? Is it okay? আবার জিজ্ঞেস করতে হবে সবাইকে। রোজিনা, are you there? রোজিনা খাতুন, are you there?
স্যার।
হ্যাঁ, বুঝতে পারছো তো নাকি আবার পরে বলতে হবে?
না স্যার, বুঝতে পেরেছি।
সহেলি আছো?
হ্যাঁ স্যার।
ঠিক আছে কি?
হ্যাঁ স্যার, বুঝেছি স্যার।
ঠিক আছে, ওকে। সো লেটস প্রসিড। তাহলে আমাদের এবার দেখতে হবে যে তোমরা আমার কাছ থেকে কি কি পাবে। এটা আমি হয়তো কালকের মধ্যে দিয়ে দেবো, চেষ্টা করবো আজকে রাত্রের মধ্যে দেওয়ার। তোমরা যেটা পাবে যে দুটো ডেটা পাবে ইন ট্যাবুলার ফর্ম, রাইট? একটা হচ্ছে ফর সিলিকন ডায়োড আর একটা হচ্ছে Schottky ডায়োড। কি যেটা পাবে যে কত ভোল্টেজ কত কারেন্ট, সেখানে দুটো টেবিল। কোন রিজনের জন্য? একটা রিজন যেখানে ভোল্টেজটা হচ্ছে লেস দেন ভি গামা, আর একটা হচ্ছে which is more than ভি গামা। এখান থেকে তোমরা কি করবে? তোমরা দুটো স্ট্রেট লাইন ফিট কার্ভ আনবে। সেই দুটো স্ট্রেট লাইন যেখানে ইন্টারসেক্ট করবে, তার থেকে তার এক্স অ্যাক্সিসের ভ্যালুটা নিয়ে তুই ফাইন্ড আউট যে what is your value of V gamma. So finding out V gamma from the curve, and you construct the curve from the data given to you. ঠিক আছে? আর যেখানে কন্ডাকশন পার্টটা হচ্ছে, তার মানে যেখানে ভোল্টেজ ইজ মোর দ্যান ভি গামা, সেইখানে যে স্ট্রেট লাইন ফিটটা করেছো তার যে স্লোপের ভ্যালু বেড়েছে m, so reciprocal of that slope will give you the dynamic resistance of the diode. তাহলে এই দু সেট ডেটা থেকে তুমি সিলিকন ডায়োড এবং Schottky ডায়োডের ভি গামা এবং আরডি ডাইনামিক রেজিস্ট্যান্স এই দুটো ভ্যালু বার করবে। সেকেন্ডটা কি? সেকেন্ডটা তোমার দুটো গ্রাফ দেওয়া হবে। সেই গ্রাফ থেকে তুমি কি বার করবে? তুমি এই ভ্যালুগুলো বার করবে। ঠিক আছে? ইনপুটে কি ভোল্টেজ দেওয়া হয়েছে, লোডের অ্যাক্রসে কি ভোল্টেজ পেয়েছো, লোডের থ্রু দিয়ে কত কারেন্ট যাবে, এবং হোয়াট ইজ ইওর কন্ডাকশন অ্যাঙ্গেল। কি করে বার করবে তোমাকে এক্ষুনি বলে দিয়েছি। ধরে নেবে লোডটা হচ্ছে 10 ভোল্ট, 10 ওহম। ফলে ধরে নেবে কি গ্রাফের মধ্যেই দেওয়া আছে, সার্কিটই দেওয়া আছে। ফলে তুমি যদি লোডের অ্যাক্রসে ভোল্টেজটা বার করো, তাকে 10 দিয়ে ভাগ করলে ইউ গেট দ্য কারেন্ট। ঠিক আছে? আর কন্ডাকশন অ্যাঙ্গেলটা কি করে বলবে? আমি তো এতক্ষণ ধরে গ্রাফ এঁকে বোঝালাম, রাইট? তাহলে এই পার্টটা বেরিয়ে গেল। আর একমাত্র যেটা আচ্ছা, এবার এই পুরো জিনিসটা রিপিট করতে হবে যখন সেকেন্ডারি ভোল্টেজটা 2 ভোল্টের জায়গায় 4 ভোল্ট হয়েছে। Am I clear? So this point number 9 given in the procedure is basically the same work but with a different secondary voltage, right? Why it is important? Because this will show you that if you increase the amplitude of the excitation voltage, then definitely the conduction angle will improve. Clear? এটা তুমি এখানে দেখতে পাবে। একমাত্র যেটা এখানে করা যাবে না, ঠিক আছে, বা করতে গেলে it becomes very difficult, সেটা হচ্ছে 8 নম্বরটা। Measure the DC output voltage across the resistive load using a multimeter. তার মানে এখানে যে ভোল্টেজটা তুমি পেয়েছো across this, that's a half wave rectified voltage, তার average value কি সেটা তোমাকে বার করতে হবে। এখন এখানেও there may be query from your side that if it's a pure sinusoid and if it's a proper rectification process, then analytically you can find out what is the average value of a half wave rectified waveform. Okay, so what do? You integrate it over the entire period and divide it by t. Okay, now in the integration you will have value only for half a period, and we know that given a sinusoid, the average value of a half wave rectified circuit is V peak by pi, if I am correct, right? If it's a full wave rectified circuit, it's 2 V peak by pi. Clear? Now the point is, still then, why I am forcing you to measure it, or why the lab manual is saying you measure it properly. So there are two reasons behind it. So can the class, right, go for a brainstorming and tell me at least one reason? We could have found it out analytically very easily, but why do we find it out using a DC multimeter? Will there be a change? And if there's a change, why there will be a change? CR Shayan, any idea?
Not quite, sir.
Huh? Priyanko, any idea? Shortly, any idea? এরা সব ফিজিক্যালি আছে না পালিয়ে গেছে?
Yes, sir.
হ্যাঁ, সোনালি বলো, কোনো আইডিয়া আছে? তুমি কি প্রশ্নটা বুঝেছো?
স্যার আরেকবার রিপিট করুন।
তাহলে ইন্টারাকশন না হলে কি করে হবে ক্লাসে? তো ভাইভাতে কি উত্তর দেবে? এখানে হচ্ছে যদি একটা পিওর সাইনোসয়েড থাকে, তাকে যদি তুমি হাফ ওয়েভ রেকটিফাই করো, তাহলে অ্যানালিটিক্যালি তুমি বার করতে পারো হোয়াট ইজ দ্য অ্যাভারেজ ভ্যালু। ইটস অলওয়েজ ভি পিক বাই পাই। তাহলে খামোকা কেন মাস্টারমশাই তোমাকে ফোর্স করছে to use a DC voltmeter to find out what is the average voltage across the load. তোমাকে বলা হচ্ছে পয়েন্ট নাম্বার, প্রশ্ন নাম্বার 8 দেখবে লেখা আছে use a multimeter to find out this voltage. The question is why? কেন এটা বলা হয়েছে? Class anyone? Tarun, are you there?
Yes, sir.
So Tarun, any idea?
Sir, no, sir.
Okay. So let's not waste our time. So the idea is very simple, right? There are two reasons behind it. So the first is to check whether the waveform is a pure sinusoid. And usually, if it's a main supply, the output is never a pure sinusoid. It gets distorted because many people are using the same supply, and therefore always there is a fluctuating load on the line. So the waveform is never a pure sinusoid, right? So if you observe it in oscilloscope, you'll find out that it's different from a sinusoid. And second thing is, since you observe, if you look at the tap points, TP1 and TP2, the tap points are the secondary side of a transformer. Okay, so the transformer might have some non-unity. It might not be a pure conversion from a value X to another value Y. So in this case, it's never a pure transformation, right? Usually never a pure transformation. right? So there may be core saturation, there may be other distortions. So the first thing is, right, the analytical value and the practical value will never match. So that's why it's always better to have the practical value. Second thing is the DC multimeter which you're using, right, that must be a correct one, because there are many scaling effects or weighting effects given in the multimeter. So if the multimeter is not really a rectifying type, then what happens? It presumes that the voltage you are impressing at its input is a pure sinusoid. So if it's a pure sinusoid, then it has a fixed multiplying factor. Okay, but if it's not a pure sinusoid, then that particular fixed multiplying factor may generate errors in the measurement. Okay, so it's always better to go for a proper measurement or maybe a practical measurement process. Use a digital voltmeter to find out what is the voltage across it. Clear? Okay. So we come to the last section of this class, where we discuss the reporting part. So there are 4 such points. So reproduce all the tabular data and sketches obtained at different steps of procedure. Calculate the cut-in voltage and dynamic resistance parameters of the 2-part piecewise linear model of both the diodes and compare them in a tabular form. So this you have to do from the graph you generate. Okay. Now using the model parameters, calculate the peak output voltage, conduction angle, and average output voltage for both the diodes for a supply voltage of 4 volt, and compare the result with the experimentally obtained values. So since I'll provide you with graphs, so the data you generate from the graph, they are the experimental values, right? But you have to calculate the theoretical values also and find out what are the corresponding, what are the essential differences between the theoretically calculated value and the practical value, right? So how do you generate the theoretical value? To generate the theoretical value, right? Let's once again go to the Jamboard. Okay, so here you see, if you look at the secondary part, oh, what a wonderful figure.
Sir, screen is not visible.
Huh? It's not visible?
Yes, sir.
Okay. So let's do something else. Okay. Just wait, I'll open up. Can you see this palette?
Your presentation is stopped.
Okay. Okay. So here, what we do, we redraw the circuit. Okay. The secondary voltage is taken to a power supply, an AC power supply. Okay. Because the secondary voltage will be non-ending voltage. Clear? And then we put a diode over here. Uh-oh.
হ্যালো স্যার,
হ্যাঁ,
আপনার প্রেজেন্টেশনটা বন্ধ হয়ে গেছে।
হ্যালো
হ্যালো স্যার,
হ্যাঁ,
আপনার প্রেজেন্টেশনটা বন্ধ হয়ে গেছে, প্রেজেন্ট স্ক্রিনটা
বন্ধ হয়ে গেছে। আচ্ছা ঠিক আছে, আমি আরেকবার প্রেজেন্ট করছি। এবার দেখতে পাচ্ছ কি?
ইয়েস স্যার।
ওকে, আমি কষ্ট করে একটা সার্কিট আঁকছি, দেখতে ভালো হবে না, কিন্তু দ্যাটস হাউ ইউ হ্যাভ টু বিহেভ উইথ মি। হ্যাঁ, দেখে তো এটাকে জুম ইন করি, জিনিসটা ড্র করা সোজা হবে। হ্যাঁ, সো দ্যাটস ইট। So this is my half-wave rectifier circuit. Okay. And say this is the load resistance RL. Clear? তাহলে এখানে ভোল্টেজটা কত? সাপোজ এখানে কি বলা হয়েছে দেখো, এখানে বলা হয়েছে অ্যানালাইজ ইট ফর সাপ্লাই ভোল্টেজ অফ 4 ভোল্ট। হ্যাঁ, এখন যেহেতু এসি 4 ভোল্ট বলতে আমাকে এসি আরএমএস বলতে হবে, রাইট? যদি সাইনোসয়েডাল ভোল্টেজ হয় তাহলে আরএমএস ভোল্টেজ যদি 4 ভোল্ট হয় তাহলে what is the peak voltage? Peak is 4√2. So 4√2 is something around 5.656. 1.414 that into 4, so 5.616, 5.656. Okay, তাহলে আমি এখানে কি লিখবো যে as if we have a power supply যার ভ্যালু হচ্ছে কত, যার ভ্যালু হচ্ছে 5.656 into sine of কত হলো? What is the frequency? Frequency is 50 hertz. So what is omega? Omega is 2 pi into 50. So this is 100 pi. বুঝতে না পারলে বলো প্লিজ। হ্যাঁ, so it will be 100 into pi into t. ঠিক আছে? So the excitation looks like this. আমি যে sinusoid excitation দিয়েছি, I have a diode and a resistance whose value is 10 ohm. So this is a 10 ohm resistance. এখন আমরা ইঞ্জিনিয়ারিং সেন্সে 10E বলি। E মানে হচ্ছে e to the power 0, e to the power 0 টা 0 লেখে না, e লেখে। So that is 10 into 10 to the power 0, 10 to the power 0 is 1, so that's 10 ohm. আমাকে 100 লিখতে গেলে কি লিখতে হবে? আমি লিখবো 100, আমি লিখবো 10E1. So 10E1 মানে হচ্ছে 10 into 10 to the power 1, so that's 100. ঠিক আছে? So this is a 10 ohm resistance. আর এই যে ডায়োডটা আছে, এই ডায়োডটার জন্য আমার এখানে কি কারেন্ট ফ্লো করবে? হ্যাঁ, এটা আমি একটা হচ্ছে কি আমার কিছু এক্সপেরিমেন্ট যেটা আমার দিয়েছে গ্রাফ, সেখান থেকে বার করেছি। আমি থিওরিটিক্যালি বার করতে চাই, তখন what I'll do, I'll remove this diode and I'll replace it by its corresponding linear model. What is the linear model? So it's characterized by a voltage which is equal to V gamma and a resistance which is equal to কত হবে? RD, the dynamic resistance. ঠিক আছে? তাহলে আমি এই দুটো ভ্যালু যদি এখানে লিখে দিতে পারি, what is your RD, the dynamic resistance of the diode, and what is your V gamma. এখানে আমি লিখলাম there is nothing but V gamma. গামা কোথেকে পেব? আমি VG at the VG. তাহলে এটা কি, যখন এই ইনপুট ভোল্টেজ এক্সিড করবে ভিজি কে, তখনই একমাত্র কারেন্ট ফ্লো করবে, আদারওয়াইজ देयर ওয়ন্ট বি এনি কারেন্ট, যেটা হয়ে থাকে, রাইট? So what is my equation? What is the KVL equation? The KVL equation is এইটাকে যদি আমি VI লিখি, this is the VI. KVL equation হচ্ছে VI is equal to V gamma plus RD plus 10 ohm into I. Sorry, into I. Is it clear, class? Okay. So that means we can always find out the value of I and the conduction angle, right, from this particular equation. ঠিক আছে, তাহলে conduction angle কি করে বার করবে? The conduction will start only when VI exceeds VG. So for the limiting case, আমি যদি লিখি যে conduction starts when VI is greater than or equal to VG. Am I clear? তাহলে সেখান থেকে কি আসছে? VI এর ভ্যালু কত? VI হচ্ছে এই জিনিসটা, হ্যাঁ, VI হচ্ছে 5.656 into sine of 100 into pi into t is equal to VG. আমি যদি সলভ করি, আমি তো প্রথম এক্সপেরিমেন্টটাকে পার করেছি। সাপোজ দিস এ কেস ফর আ সিলিকন ডায়োড, সো আই নো দ্যাট VG is equal to 0.7 volt or maybe 0.72 volt as found out from the graph. Okay, তাহলে 0.72 volt divided by 5.676 এটা পেরোলো, তার সাইন ইনভার্স দিলাম এবং তাকে 100 পাই দিয়ে ভাগ করলাম। So I find out what is the value of TG where the diode will conduct. Okay, তাহলে এরকম TG দুবার আসবে, প্রথমে একবার পরে একবার, রাইট? এই 2 into TG আমি যদি 10 মিলিসেকেন্ড থেকে বাদ দিই, which is the half wave period, I find out what is the conduction time. তাকে আবার 18 দিয়ে গুণ করি, I get what is the conduction angle. ঠিক আছে? So theoretically, from the parameters, diode parameters, namely V gamma and RD, found out in the first part of the experiment, for both the diodes, you have to theoretically calculate what are the values of the peak output voltage, conduction angle, and peak current. ঠিক আছে? তাহলে এগুলো কিন্তু তোমাদের হাতে বার করতে হবে। তারপরেরটা কি? এই একই জিনিস করতে হবে when you assume it to be a ideal rectified diode. Ideal rectified diode মানে কি? যার ডাইনামিক রেজিস্ট্যান্স 0 আর যার V gamma is also 0. ঠিক আছে? তাহলে এইটার ক্ষেত্রে কি হবে? আইডিয়াল ডায়োড মানে সে পুরো সময়টাই কন্ডাক্ট করে এবং তার এগেইনস্ট অ্যাক্রসে এসেনশিয়ালি কোনো ড্রপ না। ঠিক আছে? তাহলে ফার্স্ট এবং সেকেন্ড এই দুটো পার্ট তোমাকে বার করতে হবে ফ্রম দ্য এক্সপেরিমেন্টাল ডেটা, আর থার্ড আর ফোর্থ কে তোমায় বার করতে হবে বাই সলভিং দ্য KVL ইকুয়েশন ফর দ্য সার্কিট গিভেন ইন ফিগার 2। এই সার্কিটে KVL অ্যাপ্লাই করে তোমায় বার করতে হবে দিস ভ্যালুস। সো এনি কোয়েরি ক্লাস? So you go through the data sheets, you go through the manual, right? You go through the procedures given, and I'll send you the data tomorrow, definitely by tomorrow, right? And then from that, you try to find out what are the experimental data generated from the graphs, etc., etc. And using that you solve.
Can you please upload this document?
Huh?
Sir, upload this document.
I'll upload it definitely by tomorrow. Okay.
Okay, sir. Okay, sir.
ঠিক আছে? And the procedure is you have to submit the lab sheet definitely by next Wednesday. Next Wednesday, because the class is on Thursday. So Wednesday definitely you have to upload the lab sheets. Clear? So any further query, class? শেয়ার কোনো কোয়েরি নেই? Can we log out?
Yes.
আজকে দুজন এলে না, কারা কারা এলো না আমি বার করতে হবে ফ্রম দিস।
স্যার বলছি যে
হ্যাঁ।
আপনি তো একটা এক্সপেরিমেন্ট দিলেন, মানে বুঝলাম কিভাবে করতে হবে। স্যার মাঝে
হ্যাঁ।
যদি কোনো আটকে যায় তাহলে
তো আমাকে মেসেজ করবে, তোমার তো ক্লাসরুম রয়েছে, তো ক্লাসরুমে মেসেজ করবে, আমাকে হোয়াটসঅ্যাপ করবে, ঠিক আছে? ঠিক আছে, তাহলে আমরা লগ আউট করছি। হ্যাঁ, ওকে।